Okay. This is an important thing in practice that you have to exploit in many scenarios. And then let's come to the next question, right? How to compute okay. Well, there are two approaches. One is more theoretically grounded, but the other one is, I mean, both are well grounded in theory, but one is easier to analyze but less efficient in practice. The other one requires a bit more analysis to prove, but more efficient in practice. So, okay, so let's go back to the singular value decomposition, right? We said we have something like this. Okay. If I give you, let's say someone gave you the first singular vector, what would you do? Well, we know that if we are given V1, we can find sigma 1 is norm of x times V1, and U1 is x times V1 by sigma. Right, so remember we had, x times V1 divided by norm of x times. We did this last class where we said if I know V, then I can find the sigma and the U. Right? The only thing that we need is V, and I can infer sigma and U from that. So let's say you do this, someone gave you V1, you can compute sigma 1 and U1. How can you find the second singular vector now? What's one natural thing you can do? Yeah? You can just subtract, right? If this is your representation, if I remove this, what's the first singular vector of the remaining matrix? It's going to be V2. Right? These are all decreasing order. If I knock this out, what's left? What's the top of, what's remaining? That's going to be V2. Right? So technically, you can say to compute the second singular vector, you can say compute first of x1 equals x minus sigma 1 u1 v1 transpose. Okay, and you can do the same thing again, to compute the third singular vector. What should you do? Compute the first singular vector of x2, which is the same thing again, right? I knocked out one. If I knock out the second one, what's left? What's the top? It's going to be V3. Actually, let me write it inductively so that it becomes clear. Okay, I can iteratively peel off one after the other and keep on computing the next singular vector. Right, and this is nice because it kind of comes from this representation, right? If this is the identity that I have, if I knock this out, then what's left is this, knock this out, what's left is this, and so on. Okay. So this is one way to compute the top k singular vectors, given you can compute just the first singular vector. Yeah. Right. So that's a good question. Like, would the errors propagate? And they do propagate, but fortunately, power iteration is strong enough. Right. Remember, it kind of gets this exponential closeness. So if you run it like reasonable number of steps, it's pretty good. In fact, when you implement it, as I said, typically within like 3 or 4 iterations, it just like shoots to the first singular vector, as long as there's a gap. Okay. Even for something like the Netflix challenge data set, you don't have to run it like way many times. Any other questions? Okay. That sounds good, but the one disadvantage of this approach is you lose some kind of, abstractness. Like imagine you have a huge matrix, but it is sparse, right? Then when I do the subtraction, I lose the sparsity. Take the Netflix dataset challenge, right? Take the Netflix challenge. There we said, okay, I'm going to build this matrix, which has 500,000 rows, 17,000 columns, about, I forget, was it 100 million? No, it's 1%, right? Yeah. 100 million non-zero entries, right? You can't store the full matrix, 500,000 by 17,000. If you think of it as a dense matrix, it's 8 GB roughly. You cannot store it in your RAM, or you can store it, but it's going to just like, make everything else like very slow. Whereas if you use sparse representation, meaning only store the non-zero values, that's like 1%, right? So it's 1% non-zero entries. So meaning if this is my X, I can compute X times V reasonably well without okay. Can you hear me now? Yeah. Okay, let's hope it only went away just now. Okay, so I can compute X times V reasonably okay, even though I cannot, like if I view it as a full matrix, I can't even store it in memory, right? So I can use this matrix vector multiplication to compute the first singular vector, right? But if I have to compute top 30 singular vectors, right? I said if you ran this SVD with the top 30, it gave you a 4% improvement, and it kind of plateaus after that. After that, you don't get any improvement. Then if I define X1 is X minus sigma 1 times U1 V1 transpose, this could be a dense matrix, right? So I cannot store this matrix fully in memory because it takes 8 GB size to store down. So what can I do? Is this method struct then? Any sessions? So there are two cheats you can do. One is, again, remember, to run power iteration, you never need to know the matrix. All you need is the ability to do matrix vector multiplications. Okay. So my claim is that you cannot store X1 because it's the difference of like a sparse matrix, something which has 100 million entries as opposed to 10 billion entries. And this is a rank 1 matrix. So we can store that very succinctly. I'll just store U1, V1 separately. And then to compute x1 times v, I can do x times v minus okay. So the same trick, right? I don't need to store x1. All I need is the ability to compute this matrix vector product, okay, which I can do efficiently. Okay. So if you were to do something like this for the Netflix challenge, you have to, you can't just say, I'll compute this difference and then run SV and then run the same algorithm. You have to be a little bit more careful. Okay. And there's another approach which actually is better, but I'm not going to say why that should work. And this is called the general power iteration. And the idea here is, so in power iteration, we're only keeping track of one vector at a time, right? In each iteration, I multiply one vector with x, transpose x, and then go on. But instead of that, in the general one, you try to compute all k at once instead of peeling them one after the other. So what you do is I pick k orthonormal vectors to start with. Let me call them, okay, there's going to be two indices. So let's say V01, V02, V0k. Okay. And then for each iteration, you do this. I define ut comma 1 is sorry. It's as if you are doing k different power iterations, but all in parallel. Instead of doing them one after the other, you're doing them in parallel. And as usual, we always compute them the right way. Okay. So that's the rough idea. Like, why should I wait for one to finish and then peel it off and do something? I can try to do them all together. But then you have to be careful because remember, the singular vectors should be perpendicular to each other. Right? That's the most important constraint that we have. And when you do this, you might lose perpendicularity. Okay, even if the V's that you started out with were perpendicular, after one iteration, they may not be perpendicular. Okay. So what do? You're an optimistic person. So I'll say, okay, I'll just fix it. So let VT1, VT2, so on up to VTK be an orthonormal basis for the span of okay. So you're doing a power iteration for all k in parallel, and then you find an orthonormal basis for them, and then do the same thing again. Okay. So this also works. It's something less clear from our analysis and so on, but you can show that this also works to find the top k singular vectors instead of peeling them one after the other. Okay, does the algorithm make sense? Yeah. So kind of, but the way you would implement it, I think it makes a difference. Like the way you write it is you'll say I'm multiplying x transpose with x. Sorry. This is x transpose, then I have x, and then I have this V1 up to Vk, right? So this product is going to usually be faster than doing column, column, column. Right? It's a little bit like saying, if you're in Python, running the sum operation is faster than doing a for loop and adding up all of the elements in a list. Right? And especially for matrix vector products or matrix products, it can give you reasonable boost. Okay, and I think that boost, kind of really helps over the other gains you might get. Right. So that's a good question too, right? It can be inefficient, but K is reasonably small. So again, you can do it in time, which is like linear in the dimension and like cubic in K instead of the other way around. So you can save something there. It's not a strict, like, this is always better than the other, but I think by and large, for large matrices, at some point, this method starts working faster. Yeah. Yeah, I mean, I think that's something that you have to do. Fortunately, this is such an important problem that people have optimized this to no end. Like, as I said, LAPACK is kind of crazy. The time I had to dig into LAPACK, this was in 2006 or 2007. It's written in Fortran, right? And so we had to like find an interface from MATLAB to C to Fortran because it's so good. I mean, the package is very old, but it's still very good. It can multiply like this. It can. Back in the day, our memory was maybe 4 GB or something. Right? It could do these things reasonably fast. Whereas if you had to code it up from scratch, it would take us much, much more. Right, so they did a lot of optimization going into how do I do this matrix vector multiplication? What if I only have the handle and so on? So they were good. Okay, so there are a lot of optimizations that go into it. And in fact, let me say some other, this is not something that's like you can use, but you can imagine a theoretical scenario where this can show up. And there are some scenarios where you actually have to play with this stuff. Okay. So let me say something. So let's say X has singular values. Someone told you, okay, these are the singular values. The singular values are 1, 0.98, 0.97, 0.96, and so on. And X is symmetric. Okay, and let's say we can actually write it in this way. It has a nice sort of X is V sigma V transpose, meaning U and V are the same. So the singular value decomposition is extra nice. It's V, and then you have the singular values, which are 1, 0.98, 0.97, and so on. Okay. Now, if I try to run power iteration on this to compute the first singular vector, you're going to have very slow convergence, right? Because the gap is very small. It's like 0.02. So you have to run like 1 over 0.02 iterations to like get something. Okay? Because the gap between the first and the second is very small. When the gap is small, to converge to the first takes much longer. Right? But somehow, you can do some cheap tricks. Right? So let's say all of these other singular values are 0.97. The first one is 1, the rest are 0.98, and something is like the rest are 0.97 or something. If I look at the matrix, which is X minus 0.96 times identity, I'm subtracting a multiple of the identity from this matrix X. What are its singular values? Take a guess. I mean, exactly, right? So you're subtracting identity. Identity is the nicest matrix. So you have 0.04, 0.02, and then 0.01, so on up to 0.01. Yeah. Yeah. But identity is basically, any orthonormal set of vectors are singular vectors. So I can always subtract identity, and that only translates to shifting the eigenvalues. In this case, the singular values and the eigenvalues are the same. Okay? But again, as I said, it's a very sort of dummy example, but I want to illustrate what else you can do. Now what happens? What's the gap between the first and second? We didn't do anything. We just subtracted something, but what happened to the gap? 50%. You went from 2% gap to 50% gap. So if you run power iteration on this matrix, which is just as fast, you're subtracting something, that's it, with identity. So computing x times p is just as fast. But you would have to run 25 times fewer iterations because the gap is so much better. Okay. So you might wonder, like, okay, maybe if I find a right shift, I can speed it up a lot. And there are some tricks like this you can also do in practice. Okay. So singular values, and so the gap now is very, very good, right? So we should expect the power iteration on x minus 0.96 identity, which will converge to the same first singular vector, right? To run about 25 times faster. Okay, in fact, you can try and code it up and see too if you want. As long as the matrix is big enough, you'll see this boost showing up very easily. Okay, so there are lots of tricks like this. If you know the range of the eigenvalues, and people do the shifting operation, and sometimes there are ways to kind of shift it appropriately so that the gap gets amplified, and so on. Okay. All right. Okay, so let me discuss an application to matrix completion or Netflix challenge. And this will bring together something that we discussed a long time back as well, which is projected gradient descent. All right. So recall what was the problem, right? So in the Netflix challenge, we said, okay, you have some users, some movies, and a bunch of entries which you see. Right? Maybe this entry is revealed, this entry is revealed, this entry is revealed, like 4, 3, 2, so on. Right? A few entries are revealed and the rest are stars. Okay. So we only see, this is a matrix X. We only see Xij for some I comma j, which are in n by d. So let's say there are n users and d movies. Okay. So let me denote the set of observed entries as O. Right? O is subset of n times d. And, as I said, in the original scenario, you had almost like 1% of the entries that you see. So 0.01 fraction is what you see. You can even imagine in each row, you have about 1% of the entries that are revealed to you. It's a tiny fraction compared to the actual size. And your goal is to, complete the missing entries. And if you just did low rank approximation, that gave you some advantage, right? But what would be a even better potential formulation? Okay, low rank approximation was something that you could start with, but what else could we do to perhaps boost the error a bit? Any suggestions? Imagine that, even the unknown matrix is actually low rank. We don't believe it is true, but people do think that most real matrices like this one here is very close to being low rank. But we only see the observed entries. So what would be kind of a good sort of formulation of this statistical question? You have an unknown low rank matrix, and you see few observed entries from that matrix. You have to finish the others. What else can we do? Any suggestions? Yeah. Zero of the entries you don't see, and then, but that might increase the rank, and then we just did low rank approximation, right? That's what we did. But even when zeroing out the other entries seems a little too aggressive, right? What else can we do? Think a little bit simpler even. Yeah.
Maybe a simpler one is we drop columns or rows.
Yeah, we could do that. Let's say the no rows and columns are empty. Every row and column has exactly 1% of the empty, which is basically true because you have 17,000 things. So when you say 1%, it's roughly equally spread. Okay. As an optimizer, think of setting up an optimization problem, and then you're going to use whatever algorithms in your toolkit to try and solve it. But first, we need to come up with some quantitative optimization question that we can address. Right. So let me put the input. The input is entries of X in some matrix O and a rank parameter K. Maybe let me put a circle here to distinguish it from zero. Okay. So we see entries of X in some subset of the rows and columns O, and there's a rank parameter K. Okay. And the output is we want some X hat. That's our approximation. We want it to be of rank, at most K. But what should it optimize? What's the simplest thing we can do? Well, we only see the entries in the observed entries. So what can we try? Maybe just try to approximate the observed entries, right? That's it. I don't know what the missing entries are, but I'm just trying to find the best low rank matrix which minimizes the error in the entries that I see. Yeah.
Just make sure I understand. You're not calculating the errors for that.
Yeah, exactly.
Changing your error function.
Yeah, exactly. We're changing the error function, right? Because we don't know the other entries. Previously, we kind of used the average value there, but even that's a bit aggressive, right? So let's work with what we have and just aim to minimize the error only aggregated over the observed entries. Okay. So the difference, of course, is that you want X hat to be the matrix that you fully know and is of low rank. Okay. Does this make sense? You can't just output, your X and zeros in the remaining because that would increase the rank. You have to do something to minimize. Okay, does the objective function make sense? We have some matrix X, observed entries. I'm just trying to find a low rank matrix which minimizes the error in the seen entries. Okay.
Somehow we're assuming it's like a representative.
Yeah, not representative or something. We're basically saying, okay, for the others, I have no idea. So let me just work with whatever data I have, let me minimize the error in the entries that I see. Okay. And the intuition, of course, is that it's kind of representative sample, which is actually not true in practice. And that's one of the reasons why you have to be a bit careful, because the sampling doesn't happen at random. There's biases in how things are sampled, which we have to adjust and so on. Okay, but let's kind of just say we want to minimize error in the observed entries. We'll do with other stuff later. We'll deal with other stuff later. Okay. All right. So question. It's a good optimization problem, kind of statistically grounded, but now we have to solve it, right? Can we solve this? Any suggestions? How would you solve it? Well, the first thing is that, yeah, go ahead.
I guess this isn't a Frobenius norm anymore.
Exactly, right? That's the problem. So to go with what you're saying, if you see all entries, meaning O is everything, you see all of the observed entries, then what you're dealing with is our goal is equivalent to minimizing okay. So our goal would be to minimize, to find matrix of rank at most k, which minimizes the Frobenius norm squared error or the sum of squares error across all of the entries. And we know how to solve it, right? What solves this problem? SVD, right? The top K SVD solves this low rank approximation question. Okay. So top K SVD will solve this question. Okay, this is exactly the low rank approximation problem that we discussed earlier. Okay, but we don't see everything. I mean, that's the whole point, right? You have a subset of the entries, but is it really that different from knowing all of the entries? What do you think? How much do you think the problem would change? Minimizing the error or all of the observed entries versus some of the things, or all of the possible entries versus some observed entries? Yeah.
Quite a bit. You get a lot of degrees of freedom now.
Right. Exactly. Right. You don't have constraint on everything. So there's a lot of degrees of freedom, right? And I mean, sometimes it could even be, ill-posed, right? If I only see the first row, there may be many, many solutions, but my goal is to just find one which minimizes, right? And in fact, the problem changes dramatically. So this is something we can solve pretty efficiently. We can compute SVD efficiently, and hence we can solve it fully, right? And let me call this the matrix completion problem. Right? So you're given a matrix X and observed entries. You want to find the best low rank matrix, which minimizes the error in the observed entries. And there's a theorem that matrix completion problem is NP-hard. Okay, so when with the Frobenius norm, we get lucky, you can solve it simply with SVD. But if some entries go missing, then it becomes a NP-hard problem. Okay.
Sorry, do you want to just explain a bit more formally what is the matrix?
So basically, this is the question, right? So you're given as input X and some observed entries O, given X in O.
Oh, so this is the, oh, gotcha.
This is the matrix completion problem, right? In exactly this question, you're given this, you find a low rank matrix K, which minimizes this error. Okay. That is NP hard. In fact, it's even hard to solve it approximately and so on. You can show all kinds of hard. All right. Okay, and maybe it's hard, but let's see if we can do something here, right? You know, what else can we do to make some progress on solving this problem? Okay. To do that, let me introduce, like, what are we trying to minimize, right? So we have this function that is the one where that is what we're trying to minimize, right? So let's say, let me define L of y is, look at all of the observed entries and the error that I get. Okay, I just wrote down the objective function as a loss function. And what is our goal? You know, we want to minimize y, where y is less than or equal to k of L of. Okay, it's the same problem that I just wrote down in a more compact notation. You have a loss function and you have a set of matrices that you're trying to optimize over. Okay, this is what you're trying to do. As I said, you know, this is an NP-hard problem. And so what else can we do? Any suggestions? Yeah.
Applying gradient descent.
We could try and apply gradient descent. But when we discuss gradient descent, you could only do gradient descent for unconstrained sets. Right. So if you do gradient descent, you know, even if you start with a small low rank matrix, when you take the gradient step, you might go out of the set of low rank matrices. Right. So this is a constrained optimization problem. Right, this is a constrained optimization. Yeah.
We talked before about doing gradient descent. We could have every time we get out of the subspace project.
Exactly. So that's a very natural thing to try. You know, it might be an NP-hard problem, but you want to do something. Let's try and do that. Right. You have a loss function. Typically, you would apply gradient descent, but that's not good for us, you know, just by itself, because we really want the rank constraint to be satisfied at all times. Okay, for two reasons. One, computationally it becomes infeasible to violate it, and statistically that's what we are required to do. Okay, so the idea was, you know, okay, first idea, apply gradient descent. Okay, but you know, you can imagine this low rank set is a crazy set, right? It's a highly non-convex set. If it's a convex set, it would be nice, but you know, there's no reason. If I had two low rank matrices, there's some can have higher rank, right? So it's not at all a convex set. And you know, maybe you're somewhere here, you take a gradient step, you go out. Okay. And what do you do in such scenarios? We could hopefully project back to the set of allowed solutions. Okay, so you want to come back to the set of allowed solutions. Because in some sense, we're just using projected gradient descent. Okay, yeah.
How would you project onto?
Right. So I mean, usually projection is kind of nice. If you have a convex set, you have to do something, but you need a projection oracle now, right? So catch, what's the catch? We need a projection oracle. right?
Would it make sense to have a matrix of just like a K, like 1 to 10? Without the rest, then
Maybe, but like when you do the gradient step, you have a matrix that you're starting out with, right? I think what you're saying could also work, but at least in this case, there is a trick up our sleeve. So you might not need to do that. Okay. You're saying, let me artificially enforce that the rank is always small, but you can do that actually. But there is another thing we can do, which I think is a bit more principled. All right. And which is that. So what do we need here, right? We need a projection oracle, meaning this is, let's say you are at some iteration, let me call it, let me use y's. So you had an iteration yt, you take a gradient step, you get some y prime t. Okay. Now you had to project this y prime t back on to the low rank set, right? So how can I do that? What would give us a projection oracle? So what does it mean to project, right? So projection means find the closest matrix in my set, which is to the matrix that I'm starting with, right? Yeah. You're an SVD, right? So that's the grand kind of punchline here, which is even though this is a crazy non-convex set, we can efficiently compute projections on it. Okay. So we need a projection oracle onto lower rank matrices. But projection of y prime t is argmin of all things. That means a different letter z. Rank of z is less than or equal to k and minimizes the Frobenius distance term. Right? Okay, but we can do this by SVD. Right? So even though it's a non-convex set, we have this kind of strange coincidence that we can compute the projection by SVD. So you can combine gradient descent with SVD to get kind of reasonable approach for matrix composition. Okay. And this leads to the following algorithm. Which is which we called singular value projection. And this is from a paper with Jane, myself, and Dylan from 2009. Okay. So what we did then was, we were studying matrix completion. We said, okay, let's combine matrix, gradient descent with SVD, and it leads to the following algorithm. You start with some matrix x0, right? And you start with some matrix y0, and for some number of iterations, what do? I first compute right. I have a function here, and this is a nice convex function. You have square loss, which is convex. The loss function is convex. It's only the constraint set which is non-convex, right? So you take the gradient with respect to this, and then you compute the best rank k approximation to y prime t by SVD. Okay. So that's the algorithm that we studied, and we showed that in many cases it does work well. You can also show theoretical guarantees that unless your matrix X is somewhat non-degenerate, and in the set of entries that you see are kind of chosen at random, it works really well in figuring out the missing entry. Okay. Any questions about the algorithm? All right. And it also has additional advantages that you can exploit, kind of, you basically in terms of efficiency of computing the step, you can use power iteration in a better way by using the fact that this is a low rank matrix plus something which is sparse, and hence you can compute the matrix vector product faster and you never have to store a dense matrix. So you can put all of the tricks that we learned together and get a nice algorithm. Okay, yeah.
Right, it's sparse.
Right. So, I mean, imagine, right? So we said you see roughly 1% of the entries here, or maybe 1% entries. Okay.
Gradient is dependent on a position.
Exactly. The gradient is 0 wherever you don't see something. Right. If there's nothing there, then the gradient doesn't depend on that entry. So if the loss function doesn't depend on that entry, the gradient also is not going to depend on that entry. Right? So, gradient is 0 outside O. Okay. So in some sense, y prime t is going to be a low rank matrix. Minus a sparse matrix. Sparse meaning most of the entries in the matrix are 0. It's only non-zero when things are in O, but there's only 1%. Okay. So you can actually compute matrix vector products with this y prime t much faster. And this is essential if you want to apply this to something like Netflix data. Because as I said, it's 8 GB of memory and you don't want to ever store such a thing, if you can avoid it. Okay. Any questions about this? All right. Okay. So this is just to kind of give a, tell you that you can put all of these things together, gradient descent, SVD, they kind of work well if they need to. All right. Okay. So that's all I wanted to say about singular value decomposition and power iteration. As I said, it's a very nice and important algorithm in numerical linear algebra and across many other domains. Kind of keeps showing up everywhere where, if you want to approximate something with low rank, but you do not want to use like full SVD, then power iteration is the way to go. The other trick people use is kind of what was suggested earlier. Maybe let me just say another way is to say that my x hat is going to be a hat times b hat. Okay, I'm explicitly going to enforce that this is a n by k times k by d matrix. Okay, and then I define a loss function, which is okay. It's a non-convex function. You can compute the gradient once again in terms of both a hat and b hat, and then run gradient descent now. But this also does okay. But the earlier method has better, you can analyze it better. And in the cases where it does work, that works better empirically than this. Okay. All right. And lest you think low rank approximation maybe is not that important across other domains. One important technique that's kind of being used a lot in empirical research nowadays is, let's say, in the wild. there's this notion called low rank adaptation, or LoRa for short. So what this means is, imagine you are some company which is working on some giant model, like a large language model, right? And it's designed to do something. You have a bunch of weight matrices. If this doesn't make too much sense, that's okay. Just this is in case you ever see such a thing. Right? So let's say, you're working with an LLM, like let's say GPT-3, or and the other ones are even bigger. So let me actually say, people are doing this on Llama because it's publicly available. Now you have this huge set of parameters, 7 billion parameters, which you cannot train with unless you have hundreds and hundreds of GPUs. So you cannot fit this in. You cannot run gradient descent on all of these parameters, right? But you have this starting model, and you have a specific thing that you want to adapt it to. Maybe you want to build a chatbot on top of this, right? So you have to further tune this model to the specific learning task you have. Be it chatbot, maybe you want to program or kind of tune it to answer scientific Q&As, something in the medical domain, something in the law domain. You want to adapt it to your own data set. So what people are trying now, mainly because of computational constraints, is you have this huge parameters, weight matrices. I'm going to assume or try to change the weights by only adding a low rank update. Okay, so all of these true things are known. These are known. Like, let's say this is, I'm going to try and adapt it by some delta 1, delta 2, so on, delta depth. And these are all. Okay. You actually make it like a hat 1 times b hat 1, a hat 2 times b hat 2, and so on. Okay. You're adapting a giant model with 7 billion parameters, but reducing the rank a lot. So by doing this, people kind of reduce the number of trainable parameters from 7 billion to something like 1.1 million, 1.2 million. And it seems to give you pretty good performance. There are a lot of open source stuff, which, obviously they cannot afford the millions of dollars needed to run even a single cycle of training on these things. But with these sort of adaptations, you can train it for, I think the latest record that I saw was like, if you have 8 A100 GPUs, then you can do this training. Okay. So you're scaling down the number of parameters just because it doesn't fit into your machine. Okay. Which is kind of what you're trying to do here too. You want to be careful in how you compute the gradient, make sure that your representation is kind of compact and so on. And that's happening once again with remarkable empirical science. Yeah.
What are the deltas for?
So you have a giant model that someone gave you. You have those things, but they were trained for different tasks. Now you have your different tasks that you're trying to solve, and you think that starting from the giant model, if you make small changes to it, you'll do well. So deltas are the changes from the giant model. You are adapting it to your new task. Fine-tuning, exactly. It's fine-tuning. Fine-tuning, but the updates are meant to be low-rank adaptations, right? You can also do fine-tuning by just starting with this as the initialization and running plain gradient descent on all of these weights. That could work better, but the training is way too expensive. Okay, so that's why you play these tricks to kind of reduce the overhead. Yeah. You could potentially, that's definitely possible, right? But I think the scale is so big that like people do, even that might be too hard, right? Like I think something like Vicuña, that's one of the open source models was trained using this and many other tricks. They had to do bit quantization even further and so on. The cost was like $500, which was a big record for them because otherwise, even running a single epoch on such a giant model costs like 7 figures of cloud computing time. Okay. Yeah.
Take Laura and compare that to like actually doing the full
Mhm.
If you did fine tuning, is that something that's more expressive than doing Laura? Like, can it capture a wider class?
Probably. I mean, especially for the data sets that people looked at, you're not matching the performance of the other model. Like, one of the goals of these things was to build like a, maybe a free version of ChatGPT. And crudely speaking, they were getting maybe 75% to 80% of the preference as they are claiming it. Meaning human users were preferring the answers, or there was no significant advantage on 80% of the queries between Vicuña and like ChatGPT, but you're getting that for a fraction or tiny fraction of the cost. No, it's all just empirical, right? I mean, the computational cost you can calculate and it's much faster. I mean, just because the number of parameters is small, right? You're going from 7 billion to maybe 1 million, 10 million parameters. So that already gives you significant savings. Okay. All right. I mean, this is all, again, this is not new. As I said, this low ranks idea has been around for a long time. And the fact that if you want to do this, you can save computationally and in space has also been exploited many times before. Okay. Including in this paper, which I think it was my first research paper at some point. All right. So that's what I wanted to say about PCA, low rank approximation, and so on. And now we're going to switch gears and talk about a completely different topic, which is privacy and ML. Okay. And to do this, it's kind of, I mean, why I don't think needs much justification, but the what and how is very tricky, and we'll go over that over the next several lectures. Okay. And first, let me say, let's think of why you might need privacy in ML, right? Because first, there are many sensitive data sets. Can you think of some sensitive data sets where the leaks could be pretty devastating? Yeah.
A lot of healthcare data.
A lot of healthcare data. I mean, a lot of it also has to do with, we have various laws, right? If you're working at an insurance company, then you can only access the data from that company's laptop. If you're in California, you cannot log in outside of California and so on. There are a lot of like very strong restrictions about protecting your medical records data. Yeah.
Is this private messages?
Like, you mean messages? Yeah, for sure. Text, especially, right? What else? Financial data sets, but even somewhat benign looking things can be sensitive because of what you can infer from. Like, I'll tell you an example, an anecdote. At some point, we're thinking of doing going somewhere for vacation. My wife searched for Iceland in Google, and I started seeing ads for trips to Iceland on Facebook. Okay, that's like a giant. How did it make the connection? typically you don't want that to happen, right? Maybe you're looking for something and then suddenly all your friends start seeing ads for whatever you're looking for. Okay. So search logs is definitely a big, space where privacy can be breached in ways that we can't think of, right? It's not an obvious break in the sense that, okay, someone else is seeing an ad for Iceland. Does that tell me something? It does tell you something, right? What else? Yeah.
All your GPS records, locations you've been traveling.
For sure, GPS records. And definitely genetic data. Yeah. Facial recognition. So by and large, almost everything that we can think of has to have some kind of privacy, right? We kind of give it away, but whenever there are these hacks, the outcomes are go beyond what we think of immediate breaches, right? I mean, there's some immediate downside, but there are also downsides that we don't anticipate happening, but then they happen anyway. Okay, so let me give some examples. Right? We've talked about the Netflix data set several times, and as just as an example, and Netflix, when they released the data set, right? What was the data set again? You had users, movies, right? The users had no names. It was just like user 1, user 2, and so on. There was no completely randomized names for the movies. So there was no, maybe movies were not randomized, but you can assume even that's the case. But it's actually, no. Movies were not randomized. So the user names were randomized. Movie data, we don't care. It's public anyway, right? We know the movie names, so everything about the movie is somewhat known. So what kind of privacy break could you be worried about? They said, look, the user names are all anonymized. There's nothing to worry about. We are allowed to do this challenge. We're just releasing the rankings and nothing else. Can you think of some side effects? Yeah.
If you like movie history, movies you watched, somebody could track.
Right, but there's no name associated with any record. Right, so what could be the downside of that? Yeah.
Well, some movies might be really unpopular. Only like a handful of people watch that movie.
Right.
Then know that someone has watched that movie. Or they're probably only one of like these.
Right, but they might say, okay, we removed all of these rare movies from our data set. Now, all the movies are reasonably frequent. Every movie has been rated an equal number of times. And each user also has rated an equal number of movies. So what else?
If like they have the availability of the user, someone else has some sort of privacy leak where they actually.
Exactly, right? Many times what happens is the attack doesn't come from your own data set. It comes from correlating with something else. Okay, like what you said, those things would be attacks, but they're somewhat easy to fix. They'll say, okay, I'm going to delete these rare events. Everything is reasonably common. Everything is equal. And what happened in this case was there wasn't even a leak. In fact, there's a paper by out of UT Austin by Arvind Narayanan and Vitaly Shmatko, two security researchers in 2008. And they said, okay, this is one data set that you're saying is anonymized. But there's another data set that I can scroll and get out and crawl and get out. And there is no anonymity there in the following sense. They said, let me look at IMDb reviews. Of the same movies, and then you have user handles here, right? IMDb users, they have, some of them use their own name, they don't want them to be public, right? They're rating some movies, not all of the movies, right? So they might have rated a movie, maybe they rated Disney movies, right? Now something they seen, they thought was innocuous, they just rated those movies, right? With their own username, right? Maybe there's Alice, there's Bob, there's Charlie, or this could just be even just usernames of various people. This is something that you can publicly take out, right? You go to a movie, you see a review by a user, you can click on the user and see what other movies that user has reviewed. Okay. And instead, by looking at kind of almost playing some simple tricks and matching the ratings, okay, they could identify users between these two databases. Okay. For a significant number of people, they could identify which rows in this anonymized data set corresponded to which rows here. Even one person's leak is atrocious, but they could do it for many, many people. Okay, they could match, like, okay, this anonymized row corresponds to Charlie. Kind of makes sense, right? If there are 10 movies, 2 people are unlikely to have the exact same rating. They might be similar, but no one's going to say, okay, this is 4, this is 3, this is 3.5, and so on, right? And they use some metrics and some nice tricks around that to do this matching. Okay. And now this is a privacy break, right? Why? As I said, maybe Charlie only wanted to rate or reveal how much they liked or disliked Disney movies. Okay. But now here, this data set might have many, many movies which were meant to be private, but are now known to everybody. Okay, you understand the issue? Like, okay, I'm fine with publicly revealing that I hated all Marvel movies, but then I don't want others to know that I like all DC movies. Maybe that's a logical conclusion or not, but whatever. Okay. Okay. And this was a real attack that happened. People did this reverse engineering. They broke the privacy by connecting the name, which users were which, and they learned movie preferences of various people for movies that did not want to review. Okay. Here, you can argue that this is publicly revealed information, so the users made the choice. When you connect, they did not make the choice, and Netflix is violating their trust, their guarantees, right? And in fact, after Netflix Challenge 1, they announced, once that ended, they announced Netflix Challenge 2, which said, okay, there were several people. In fact, there was almost like a website where people started like open sourcing and collaborating across the internet to try and get to this 10% benchmark, right? If you get to 10%, you got $1 million. I think the first team to get there was a group from AT&T Research Labs. Once that was done, they said, okay, we'll incorporate some of those things into our new prediction system. And then the challenge 2 said $10 million. If you beat the new one by 10%, and I think there's a time limit of like a year when it would end. Okay. But once this paper came out, they had to cancel the challenge. Yeah. So there was, the first one was a group from AT&T Research. I forget who their names were.
The SVD.
I think they use a bunch of things. At some point you can get to like maybe 6 or 7% using principled ways. But by the time I entered grad school itself, it was just like getting very, very hacky. Like people were doing ensemble training where, I have a method, you have a method, 10 different people have 10 different things, but each one on top of the other, kind of bootstrap on top of them. And that was getting to 9%, 9.5%, and so on.
Like an engineering.
It's not clear, right? Because at that point, you could even be very, very fine tuning to the specific data set. And I'll talk about that a little later too. There's an issue there with leaderboards and so on. Okay. But this was, they said, okay, this is the next step, which is $10 million, but then Netflix had to cancel it. Because of a lawsuit for violating privacy. They couldn't go and say, okay, I'm not violating privacy and I'm just making it anonymous, because this paper showed that you can do this attack. All right. So that's one sort of, one non-trivial place where you might be thinking, I'm just doing something that I'm learning, everything looks kosher, and nothing bad's going to happen. And another very fun example that I like is, for there are numerous examples, but I'm just relating two which I think are funny. And I mean, this one is very nice, but it shows this correlation attack that you might imagine. The other one is, this happened with Massachusetts state government. Let me not try to spell Massachusetts. So they wanted to release medical data for patients using health insurance, right? State health insurance and so on, with the nice goal that, if you want to design various drugs, or, we want to design or estimate how various treatments are working, it's good to have data available widely, right? Instead of only one, particular group or one insurance company owning it, it'd be good if it's more widely available. Okay. So William Weld, who was the state governor, he said, if something along the lines, I'm paraphrasing obviously, something along the lines of, okay, if you are using state-funded money, the money from the state government or the federal government to do some kind of research and collecting data sets, you should make your data set publicly available, right? Seems logical, rational, for the good of the people, right? Okay, but what's the kind of data sets that these people collect, right? You have maybe name, email, address, SSN, all kinds of stuff, date of birth, and then many medical stuff. Right? What's your height, weight, how has it been growing? What is your, how is your blood pressure over the few years that you have, maybe some other markers and so on and so forth. Okay. They took all of this data and they said, you can release just the medical stuff right here, and then kind of erase this part. Let me black out these things. I think they released the year because for data of birth for medical records, it's important to know the age of the patient. And without that, most of the data, it's a very important feature. So they had all of that. So the governor, William Weld, passed this law, and all of this data sets started becoming available. Right? And guess what happened next? Any guesses? Sorry? But actually even very funny. There was a grad student at the time at MIT. Forget her first name, Sweeney, I think Latanya or something. And what she did was she looked back at where the governor was born, his age, and so on, and mailed the governor his health record. Kind of funny, right? That you think this is all private, but you can actually identify with using few things, like when you went to high school. She figured it out just by kind of whatever publicly available information there was about the governor. Again, from other sources. If you had only this data set and no other data set in the entire world, even then there will be issues, but at least it will not be as bad as this. Okay. So these are all kind of called reconstruction attacks. Somehow you're trying to reconstruct what's in the data set by using or aggregating across various sources. Okay. All right. I mean, all of this suggests, I mean, even AOL, there are many, many other stories. Like AOL had this thing where they released a lot of emails, masking out like the user IDs, but then someone went and identified a person explicitly and said, these are all of our emails for the last few years and so on. Okay. So the question we should ask is, how to get guaranteed privacy. Okay. So I should say the first thing about privacy is that the only kind of privacy that you can get, I'm saying this as a kind of a qualifier, but really it's not even a qualifier. It's meaningless to say you have privacy if you don't have guaranteed privacy. So for learning, if you think of applied machine learning and so on, your method might not have good theory behind it, but you can say, okay, I'm getting good performance in practice. Here's your data set. I did my test error, my training error, and my prediction accuracy is small. I'm getting 90% accuracy on ImageNet. Go beat that, right? That's an empirically verifiable thing, right? But saying what you're releasing preserves privacy is not empirically verifiable. How are you going to say that no one is going to be able to, how are you going to demonstrate that you have privacy empirical? You can demonstrate accuracy empirically by having a holdout set or many other things, but for privacy means proof of privacy. You can't say I couldn't break it, so it's private, because someone else could break it by using other data sets, using maybe faster hardware or a clever algorithm, right? Any question?
Good, but by like having some guarantee on the
That's what we have to figure out, right? But at the end of the day, you can't just kind of, once you release the data set, you can't demonstrate empirically that you're going to be withstanding at various attacks. Okay, you have to do something theoretically guaranteed. Okay. So this is an area where proof is the real deal, not just like after the fact, I'm okay with performance, even if I don't have a proof, I'm okay. That doesn't work in privacy. Okay. So with that as a goal, let's take step towards some basic questions and answers that we can get. Okay. The first thing is how to model privacy. What can we guarantee? What can we get? And you want to make it obviously useful, right? And in fact, I should say, for instance, here, after this happened, NIH, which also said that, if you're collecting data using federal funds or you're conducting a study using federal funds, then your data set should be publicly available. They removed that law, that restriction, after these sorts of attacks happen. Okay. But then you can imagine that's bad, right? Because you want all groups to benefit from research. Okay. So there's this trade-off that we have to find the sweet spot for. So to get us started, let's start with a very simple goal. And okay. So I'll say first example. If you're thinking of machine learning and so on, let's forget all of that. Let's think of the simplest statistical task that anyone can imagine. Any guesses? Something very, very, very simple. Well, okay, so let me say it because they're very simple, many, many simple things. So I might be looking for something very specific, which is like, let's say you want to find out what's the average age within a group. Yeah, just come to the average of something, as simple as that, right? You had a question or?
Oh, no, I was about to answer, but you were.
Okay, so just like, something simple, right? Just compute the average. It's not even like an ML problem. You're not trying to solve something learning, but just aggregating is some statistic about your data set. And in this case, I'm even saying the data set only has, for each person is a single feature. Maybe it's the age, maybe it's the salary or something like that. I want to compute the average salary, average age. Right? So compute the average So maybe to make it even simpler, let's say you have person 1, person 2, up to you have n people and age, salary, that's, let's take it, make it even simpler and say each person has a preference, right? Has a variable which is 0 or 1. Okay, do they like ice cream or not, or something like that? Okay, that's the only thing that we are interested in. And in fact, it's not as far-fetched as you might think. It could be a preference, and what we would like to know is how much do people like it on average, right? Maybe you're showing an ad to millions of people. Some people are clicking it, some people are not clicking it, right? Xi denotes whether or not that person clicked on that ad or not. And you want to know what's the click-through rate of this ad averaged across all of the people, right? Okay. So what we want is estimate or calculate, let me say P, which is the average value of these 0, 1 valued numbers. Okay. That's what I want to do. And imagine you want to release this information somehow so that people can infer the average, but not learn too much about it. Again, since it's a toy example, we have to think accordingly, right? So what's the silliest maybe not silliest, let's say. Obviously, I could release all of the data as it is, and that gives me no privacy whatsoever. Okay. And if I want full privacy, what can I do? Yeah. Well, you have to release something. Let's say, for each person, we have to release something which looks like this. Okay. Something along what you're saying is I'm just going to put random values. Right? It's as good as releasing nothing. I'm just putting junk values. Nothing to do with what you started out with. Okay. So yi is completely random. And this is something that happens in survey questions, right? Let's say you're trying to find out like political leanings within a state by making random calls and asking survey questions and so on, right? They'll say, okay, do you like this candidate or not? Do you like this candidate or not? And so on. You get this information, then you want to find out how popular is this person. So you have to release something like this. Okay. So this is no privacy, there's full privacy. But the full privacy is completely useless for us because then you cannot compute any meaningful information from the data set. So what can we do? Yeah.
You keep like the same value set, but. X1 to Y2 or X1 to Y5.
Right. So somehow you're saying permute the things or so that the average remains the same, but you get a different looking data set. Okay, that's a good idea.
Could calculate maybe the mean and the variance of the data set and then generate.
Right. So you can generate a new data set like that too. But as I said, that will solve definitely the story question. But imagine that, just as a lead up, maybe a person, you release this data set, you are a survey company, you're going to release this data set, and there are various analysts who are trying to use your data set. Right? And they'll say, okay, maybe I want to know how popular is this person in Texas and how popular is this person in California. Okay, that's something that you didn't plan for. Right? That wouldn't solve that question. And the same issue would show up with what you were suggesting. Right? Yeah.
I don't know if this is too fuzzing.
Right. Fuzzing seems like a reasonable thing because maybe, the analyst could still at least do something like what she wanted to do before. I want to know the average within California, maybe in the southern states, maybe in the northern states, something like that, right? There's some other thing that she wants to do that could still be manageable if I don't just completely ignore what these XIs are, but fudge them a little bit so that it's not very clear what the actual value is, but it's still somewhat useful. Okay. Yeah.
Know that we were always trying to compute.
Right. We're trying to compute the average function, but let's say we don't know which set among, to compute the average on. Right. Maybe I'm looking at a subset of these things, subset of people who are in some location, and I want to compute the average value there. That's different from computing the average across the whole data set. So it's still trying to compute the average function, but on a restricted subset. Does it make sense? Okay. Again, as I said, we're just kind of even building up the right question to ask. We're not even sure what's the right question to ask, what we can hope for. Okay. Yeah.
In a case like this, we're taking the average, and then we how much each data point is affecting the average. We want to remove in some ways, if you figure out what data point is affecting the average,
right,
that kind of gives away information about the user.
It could definitely, right? So the way we are going to release the data set, we should take that into account somehow. Okay, and we should think about that. But right now, let's even formulate what we want to do. It's not clear, right? Should we first think of the way to release it or the right guarantee that we want? All of these things somehow have to mix together, right? Okay. So at least in the context of surveys, people have been studying it back from the 60s itself, and there's a middle ground between these two, which is called randomized response. Okay, and this is due to Warner in 1965, who introduced this nice model and said, I'm going to release something that looks like this. I'm the survey company. I ask each person whether they like this candidate or not. But then with some probability, I'm just going to throw that answer away and output garbage. It's basically kind of interpolating between full no privacy and completely random values. Okay. So imagine for each person, I say, okay, with probability 0.1, I'm going to output the correct value, and 0.9, I'm going to output a random value. So there's some correlation between the true values and what you observe, but you can fine tune it now. It's like there's a wheel that you can control how much it correlates with the true answer. And perhaps you can use this to understand the privacy somehow. Okay. I think this is one of the first ways where people did something to data with privacy as a goal. Like one clear objective of this was to try and get some kind of privacy guarantee. Okay. So Warner, 1965. I think this is from statistics community, really. And for each user, I output yi, which is xi with some tunable parameter gamma, I'm going to output the true value with probability half plus gamma and output the opposite with probability half minus. Okay. So if gamma is half, then I'm getting basically the exact value, right? So that's the no privacy setting. As gamma increases, my privacy decreases. And if gamma is 0, what am I outputting? I'm outputting completely random value, right? It's probability half is 0, probability half it's 1. So there's no correlation with the input, right? So this corresponds to gamma equals half, and this corresponds to gamma equals 0. So smaller gamma means better privacy. Okay, that's randomized response. Randomized response, meaning you ask a true question, but then what you release is independently randomized for each person. Okay. So say gamma equals 0, full privacy, gamma equals half, no privacy. All right. Yeah.
I'm not convinced that the gamma equals 0 case.
Okay, why?
I mean, suppose you had the gamma equals 0, you're outputting xi is between 0 and 1. If you know that see like either like 0.9 or 0.1, how extreme.
No, but if gamma is 0, what's happening, right? So both of the options, 0 and 1, are happening with probability half. So it's full privacy in the sense that it doesn't depend, the output distribution doesn't depend on the input distribution at all, right? Even if everyone was 0, the output distribution will still be the same as even if everyone was 1s.
Right, but you know that everyone can't be 0.5.
I mean, it could be, right? So think as a Bayesian, given this sample, what prior can I have? Nothing. It could be all zeros, it could be all ones. In all of those cases, I will see the same distribution. It's like, if there's a box behind, right? And what I see doesn't depend on the input. So I should not be able to learn anything about the input.
For example, if all your inputs were 0.
No, there's a numbers, they are either 0 or 1.
Oh, okay.
Yeah, okay, I see what you mean. You're talking about this, right? Yeah, they're either 0 or 1. Yeah, we're looking at the easiest case, right? This is a survey question, yes or no answers. Okay, yeah. Good point. Yeah. Any other questions? All right. Well, we have something, it may at least, we know that this is some parameter we can tune between these two things. And let's try and figure out, depending on our privacy budget, we can do something. Okay. But how useful is this? Okay. Now you release this data set of, should I say, okay, let me put bars here maybe. Okay, so I'm going to release this publicly. How useful is this compared to the original thing versus releasing completely random things? How useful is it? We can, how would you measure utility, right? Especially if I'm only interested in computing the mean, how could I measure utility? Yeah. It's something we are tracking. You can assume it's known to the attacker.
In that case, when we take the average, the expected value of
Yeah, so let's exactly try and do that, right? So how would you measure utility? You would wonder if, can I use this new released data set to kind of compute some estimation of the true mean? Okay. So how useful is the new data set? Well, can I get a good estimate of the true mean? Okay. And as was suggested, we should not just compute the average of this xi bar. We have to do some correction because you added this noise. Okay. So to figure out how to correct, and let's assume you know the gamma, how would you correct? Let's see. See, we said xi bar is xi with probability half plus gamma and 1 minus xi with probability half minus gamma. Okay. So what is the average value of xi bar? You can just compute it, right? It's half plus gamma times xi plus half minus gamma times 1 minus xi. So this is okay. So we have this equation and you have this xi bar values. How, how could you estimate the true average of the xi's given the xi bar values? Any suggestions? I'm seeing these xi bar values. I know the gamma. How can I sort of correct and guess the true mean of the data set? Yeah.
by the half minus gamma.
Right. So, I mean, if I kind of reverse engineer this, I get this equation. Right? Okay. So in other words, okay. So if I just add up everything and divide by n, I kind of get a similar looking equation. I just have to compute the average on my new data set and shift and scale it up appropriately. Okay. So if this is my true mean P, and this is my estimated value P bar, this is the estimated on the released data set. Okay, so you had the original data set that you collected, but you're not releasing this to people who are looking to perform various kinds of analysis on the data set. You're releasing the xi bars for public consumption. Okay. And you can estimate the true mean by looking at this P bar. Okay. So ideally, we would like P bar to be somewhat close to P still. And the higher the gamma, the lower the gamma, the better privacy each user has. Okay. So what can we say about how close P will be relative to P bar? Intuitively, what should happen as n increases? Should you get better and better estimates or worse and worse estimates? Better and better, right? If you have 1,000 people, your estimate of the average is going to be better than if I only let's say I'm trying to conduct a survey and find out the average age across the United States. If I query 1,000 people versus 10 people, the 1,000 people will give me a better answer, right? And there's various, kind of standard techniques and statistics to quantify it. And I'm just going to state one without proof here. Let's say this is stat 101 is you can show that the true value P minus your P bar is greater than epsilon is less than or equal to okay. So the chance that the gap between my estimate and the true estimate is more than epsilon is something like this. Okay, this is something you can prove by computing the variance P minus P bar. Okay, if you can compute the variance of P minus P bar, apply Chebyshev's inequality, you get something like that. Okay, but let's just take it for granted. We're going to do different things soon, so I just want to give a ballpark estimate of what's happening. Okay. And let's, just to kind of get a sense, suppose I want epsilon accuracy with at least 90% chance. Okay. So I want to make sure that my accuracy is going to be within some epsilon, like let's say 0.01 or 0.1 or whatever, something like that, with at least 90% chance. I want to say with reasonable certainty, my estimate is going to be close to the true estimate within some error. Okay. So if I want this, then I should set, to simplify the arithmetic, let me say 75%. Okay. Meaning I want this chance to be 1/4, right? Or less than or equal to 1/4. So to do this, to achieve this, we need as epsilon increases, as epsilon decreases, the probability should increase. Yeah. So let's just interpret this statement, right? It's saying, suppose I take the randomized response with like gamma is 0.2 is something that I as a person am comfortable with. Right? Someone says, okay, your answer will be thrown away with this much chance or will be flipped, then maybe I'm okay with 0.2% or 20%, or maybe some, okay, that's too revealing for me. Maybe someone will be comfortable with like 40% or something. But it's something you can quantify, right? You can say each person, the guarantee that I'll have is your answer will be flipped with this much chance. If you're comfortable with it, answer the question, right? And this is something, one of the most important things in privacy is you might have various guarantees. You can debate later what those guarantees are and so on, but you should quantify it. It should be precise. You can't just say, okay, anonymize the names and now you can't do anything. Right? If you can quantify it in some way, then each person can make their own decision. I'm comfortable with 20%, I'm comfortable with 10%, and so on. Okay. Anything quantifiable is what is highly desirable. Okay. And if you know the accuracy epsilon and the privacy parameter gamma that you're comfortable with, then this tells you how many people you need in your data set to achieve that. Right? So the more questions, more people you have, the better the privacy you can guarantee for each individual, which again makes sense intuitively, right? Yeah.
These cases is the gamma parameter release.
Is known to us. Yeah, it's known to us because we're saying, okay, here's the data set, and this is the gamma that I used for it. Because otherwise you cannot do the correction, right? The correction heavily depends on this. And people actually implement this, especially in some servers. Randomized response is something that people do. Okay. Any questions about this? And I think it's a reasonable substitute for individual privacy because you're saying my answer will be thrown away with some chance and replaced with a random thing. And with some chance it will survive, but that's okay for me. Because that's the amount of risk I'm willing to take. Okay. And if if I have 1 million people, then I can make gamma very, very good. I can guarantee very good individual privacy as the number of people increases. Okay. Any questions about this? All right. So it's quantifying privacy in some way, and is also telling you how big a data set that you need to preserve this privacy. All right. So what we would need to do going forward is define some quantitative array. Or let me say, define some way find a way to quantify privacy. This is number one. And then there are two sides of the same question, which is how much does this affect the accuracy of the model? I do this privacy, then you can imagine doing this noise to images or whatever you have. How is it going to affect the accuracy of the models that I'm going to train on? Okay. How will it affect the accuracy? Okay. But usually in the context of privacy, what you do is it's more useful to ask the flip question, which is for a fixed accuracy parameter, statisticians prefer this variation, and I fix the accuracy parameter epsilon. How big should my data set be to have the privacy guarantee? and the accuracy. Right, I mean, both of these are the same. How will it affect the accuracy? If you know that, then you can reverse engineer and find out, okay, if my allowed accuracy is, am I allowing myself an accuracy loss of 0.1, and my privacy parameter is something, or my desired privacy quantified way is something, how big should the data set be? Okay. And typically, we think bigger data sets is better for individual privacy. Okay. And in the next class, when we come back, what we will do is look at one of the more useful models in privacy, more useful, well-studied, and more broadly applicable than many other models, which is differential privacy. Okay. And as a base model, I think it's a very good model. It captures many, many things. Obviously, it becomes too restrictive for some applications, but we'll talk a little bit about them later. Okay. All right. So that's what we'll do in next lecture on Wednesday.